Hi everyone, my name is Cha Cha. Welcome back to my channel. Today I'm going to be going over some functional groups I think are really important for the MCAT. Just in general, I feel like functional groups are really important to understand for organic chemistry because if you can understand functional groups, you can recognize a lot of the patterns that you'll see in MCAT. So the first functional group that I would like to go over is alcohols. Woohoo! So alcohols, they can hydrogen bond. So the acronym FUN, hydrogen bonding is fun, ha ha ha. But so fluorine, oxygen, and nitrogen, they can all hydrogen bond just because the electronegativity difference between those atoms and hydrogen is so big that it almost has like some partial ionic bond characteristic to it. So what do I mean by that? So over here I have a little diagram. So like fluorine, um, well, 95% of the time, do you see the little green electron here? That will be in fluorine's orbital, whereas 5% of the time it'll be in hydrogen's orbital. So that means that like fluorine almost has like a full octet for the most part. That's why it's so stable, such a high boiling point and melting point. I also want to talk about some diols that you'll see. So geminal diols grouped together. So that means that the alcohols are the hydroxyl groups. They're on the same carbon, whereas bicynyl diols, they are on adjacent carbons. So then I have the prefix hydroxy, and then ol. That's a suffix that you'll often see for alcohols. So additionally, I have this little molecule that I have. So it has an alcohol group, which is over here, and then I have a carboxylic acid. So when you put two and two together, carboxylic acid, because it's the most oxidated functional group, it'll always have the highest priority. So instead of having this be labeled, the parent chain be labeled 1, 2, 3, 4 in this light green, that's not right because it doesn't have the highest priority functional group at carbon position 1. So the highest priority functional group, which in this case is carboxylic acid, will always be placed at position 1. So in this red, that's the right. So it's 1, 2, 3, 4. Red has the right order for that molecule. And here I have some further naming stuff. So this will be 1-propanol, this molecule. So it has 1, 2, 3. So it has 3 carbons. So that means it'll have that propane and then ol instead of like the ane, it'll be replaced with because it has the alcohol as its highest priority functional group and also the only functional group that's in this molecule. And a lot of the times on the MCAT, you'll see a lot of the times they'll try and trick you with like the length of the parent chain. So a lot of the times there'll be two answers that'll be like completely off for the parent chain. So for in this case, I have like 1-butanol. So you know that's not going to be right because butanol, that's for 4 carbons. And you don't see a fourth carbon here. So right away, you could probably knock out two of the answer choices. And if you're not entirely sure which functional group is, at least you have a 50-50 shot compared to that 25% originally. Now I want to go over some of the oxidizing reagents that you'll see, specifically for alcohols. So PCC, it is a quote unquote prude because it doesn't go all the way. So it doesn't go from that primary alcohol, which I have here, to that carboxylic acid, which I have here. It stops at aldehydes, that's that carbonyl group. So it won't it won't like further oxidize that hydrogen. So it'll only to create that hydroxy group, it'll only have oxidized to that carbonyl and then it just stops and won't go any further. And then KMNO4, it also goes all the way, and then K2CR2O7, that also goes all the way. So whenever you see a bunch of oxygens in a reagent, assume that that substrate, like your substrate that it's reacting with, it'll get oxidized. So because that reagent, for example here, it typically will have a high oxidation state. So it'll be often paired with a metal. So for in this case, K2CR2O7, chromium has a +6 oxidation state. That's really, really high. So it desperately wants oxygen. It's not oxygen. It desperately wants electrons in order to satisfy that and to make that it go down at least the oxidation state. So it's readily accepts electrons, which means that oil rig, right? Like oxidation is loss of electrons, so that means that that substrate will get oxidized, while the oxidizing reagent is what will get reduced. Now I want to go on to ketones versus aldehydes, Batman versus Superman. So over here, I have the ketones. So ketones have a suffix that'll end in "-one," which ketone, so that makes sense for a suffix. Whereas aldehyde, their suffix or the end of the molecule will be "-all," which makes sense since aldehyde, aldehyde. And then so for the prefix, they can either be oxo for ketone and aldehydes, whereas ketone also has the additional prefix of keto, which makes sense since it's a ketone. So ketones you can't oxidize any further just because where are you going to go? Like there's no hydrogens. These are just carbons that are attached to ketones. It has two R groups, so nothing to do there, right? Whereas aldehydes, you have that hydrogen group attached to the carbonyl instead. In the example, so I have some naming examples. So for ketones, it is 2-propanone because there's 3 carbons, 1, 2, 3, and then that carbonyl is at position 2. So that's where the ketone will be. So it's 2-propanone, whereas this would be ethanol because it's 1, 2. So there's 2 carbons, and so it's that where the ethane comes, and then it's aldehyde, so it'll be ethanol. Um, yeah, and then also real quick, I want to go over like what an alpha carbon is and a beta carbon is. So an alpha carbon will be the carbon that is directly attached to that carbonyl. So it'll be like have a positive charge because oxygen is it's more electronegative than carbon is. So it'll draw the electrons closer to itself, leading to that carbon having a partial positive charge. And that beta is the carbon that is adjacent to the alpha carbon. So if you think about the Greek alphabet, that makes sense, like, right? It goes alpha, beta, so 1 and 2. And then, so aldehydes, they're more reactive than ketones are because they have less steric hindrance, right? Because like the ketone, it has 2 R groups, whereas the aldehyde only has 1 group. So it's easier for reagents to get on into aldehyde's business. And then some of the reducing agents that I want to go over. So there's the nickel one, and the nickel one, it only reduces ketones and aldehydes to alcohol. So this is really important. Whereas the lithium reducing agent, it'll reduce everything with an oxygen to alcohol. So like your carboxylic acid, your esters, et cetera, et cetera. So here I have an example for a ketone that's getting reduced to a secondary alcohol, whereas this carboxylic acid will become a primary alcohol. So why are hydrogens like is there a common theme of having like these metals with paired with these hydrogens to be a reducing reagent? So um remember that metals are less electronegative than hydrogen is. So hydrogen is anionic. So that means that hydrogen has all those electrons, right? Because it's more electronegative. So hydrogen is going to keep the electrons closer to each other, which is not very stable. So that hydrogen wants to react as quickly as possible. So what'll it do? It'll react with um, something that'll readily take its electrons, which is those oxygen groups, or like that carbonyl for on that oxygen group on that the carbon the alpha carbon on the carbonyl. Oh my gosh, words. So anything that's like partially positive, we'll take that. So right, since positive and negative they attract, and then that carbonyl, that alpha carbon has a partial positive charge. I also really want to go kind of over into protecting groups, and I have a little bit more further down. But first of all, I want to talk about what are acetals and ketols. So in acetal, and ketols are stable under basic conditions, and I'll get into it in a little bit as to why that is. And acetal, hence the name, with like aldehyde for A, I guess they both share. So as you can see, it has two oxygen groups that are attached to it, or esters in a way that'll help protect it. So like if you're trying to do some reaction, but you don't want to have the ketone or aldehyde react, then you could add a protecting group into it. And protecting groups are really easy if you just add an acid. Um, then they are like hydronium, for example, like they'll just revert back to the original form. Whereas ketol, that's a ketone form of the protecting group. Then hemiacetals and hemiketols, they are unstable because they have a hydroxyl group instead of like the ester additionally. So they will not really protect you that well. This is typically a intermediate in a reaction. So what are uh protecting groups? So it's not just so it protects ketones and aldehydes. So like for at least this example that I have, and it requires an acidic catalyst. Typically, it has an acidic catalyst, so that makes that alpha carbon even more positively charged because if that oxygen has a positive charge, then that carbon it'll donate even more of its electrons towards the positively charged oxygen in order to negate some of that charge. Because if you have a positive charge on an atom that is electronegative, then that makes it super, super unhappy. So it's really greedy. It's throwing a tantrum. It's collecting all of the electrons towards itself. So once that's in there, then you could have my little like esters here. Excuse me. It can go in and it can attack, that nucleophilic attack of the alpha carbon. And then you'll end up with a structure like that. So it's stable under basic conditions, right? Because like you're not going to change anything if you have two electro nucleophilic atoms to begin with. Like it won't be unstable. Whereas if you were to add a hydrogen, I don't know why this keeps, that's okay. But if you were to add a hydrogen, right? Here, then that'll make it unstable because you no longer have two lone pairs on the oxygen. You will have three lone pairs and, sorry, not three lone pairs. You'll have three bonding pairs and a lone pair, which is not great for oxygen. Now I want to go over carboxylic acids, which is the suffix oic acid. They are the highest priority, primarily because they are the most oxidative. Um, sorry, they are the most oxidative functional group. So they are the most reactive alpha carbon. So I want to go over two like common names that you'll often see, and it's not just specific to carboxylic acids. You'll have formic acid. So F for formic, think first. So it is one carbon. It is also known as methanoic acid, this example. You also see like formaldehyde, for example, like that'll just have like that one carbon. And let me draw it out. So this will be formaldehyde. For example, it has that one carbon. Same here with formic acid. And then acetic acid, right? Two carbons. And this IUPAC name, I should say, which is like the international like standards for naming molecules, is ethanoic acid. Um, yeah, so typically carboxylic acids will have like the highest melting points just because they can also hydrogen bond. And then, as I was talking about earlier, right, like I have the reducing agent, so lithium will fully reduce it to primary alcohol. And then, is this a basis? It's like a blueprint for a lot the rest of the functional groups that I will talk about in this video. Um, Here I have esters, and they have the suffix OAte. So like carboxylic acids, but they have OAte instead of the acid. So like I have oic acid, and they also have like the YL. So think of like when you're naming a substituent for like an alkane, you'll have a YL. So you'll have like it'll be methyl instead of methane, right? So kind of think about it like a substituent. Whereas O8 is like the main part of the ester, so I kind of think about that as a parent chain. So that's like where the carbonyl will be, which I have in dark blue here. So whenever you see like the carbonyl, oh yeah, that's the parent chain, so that'll have the O8. So what do I mean by that? So like in green, I have the ethyl. So that's one and two. So it's ethane, so it'll be ethyl and then propanoate because it has the carbonyl here. It'll be, and then there's one, two, three carbons. So that's propanoate. So propane to propanoate. And then I have the Fischer esterification. So this is just essentially a fancy way of saying how esters are created from a carboxylic acid. So here I have my carboxylic acid, then I'm adding like an acid catalyst. Now that carbonyl, the alpha carbon, is even more positively charged, so it's even more reactive. So then you'll have an alcohol come in. More specifically, this is methanol because it has one carbon. And then that OH group or hydroxy group will come in. Now it's just like really unhappy, right? So so it opens up that carbonyl. So now that the carbonyl carbon is now happy since it has two lone pairs now, whereas the alcohol is not happy, right? Since it has three bonding pair in one lone pair. So it's positively charged. So some base will come in and it'll take off the hydrogen from the methanol. It doesn't have to be the original alcohol that you were using to begin with, like that methanol could be some other base. But and then basically that one of just through chance, since a lot of times it's going through different like phases of itself, like that oxygen can come in and it can collapse and it can kick off the other leaving group. It can like find that little bridge, kick off that leaving group. Now you're left with that carbonyl again, but it has three bonding pairs and one lone pair, so it's unhappy, right? So then that base can come again and it can take off that hydrogen from that carbonyl, no problem. And then you're left with an ester. Woohoo. Then I want to go over amines, which is N-amine. So whenever you see something that's a substituent for an amine, you'll see the N in front of it. So amines are like esters, but instead they have a nitrogen instead of an oxygen. So here I have N-ethyl, N-methyl, butanamine. I don't know why this is blue. This should be red. Um, so remember when you're naming stuff, remember that you always want to go for the substituents and just in general, you always want to go in alphabetical order. So I have my N, so A, B, C, D, E, ethyl comes before ethyl. And again, right, since like your parent or which will have the amide in it, that will be what has a carbonyl. So one, two, three, four, so that's butanamine. And then over here, we'll have our parents, or sorry, our substituents. So we have one carbon, so it's N-methyl, whereas one, two, so it's ethyl, N-ethyl, and methyl butanamine. And then let's go to anhydrades. So it's oic anhydride. That is what the suffix will be. So they tend to be cyclic, so esters can also be cyclic too. And then you replace an acid, the acid for oic acid with anhydrate. That's all it is. So you're literally smashing together two carboxylic acids, and that is how you get anhydrates. So the an/a in anhydrates, that means without. So while hydro means water. So you could essentially mean that anhydrates, like when you're smashing the two carboxylic acids together, you're gonna get rid of the water molecule. Also sad for the water. But that's what a name means. And it also makes sense that in order to break up anhydrates, you're going to add water to reverse. So hydrolysis, which is what I have here. So breaking it up, get those two carboxylic acids again. So basically, um, you're just going to count how many carbons there are. So in this one, there's one, two, three. So it's ethanoic. And this is one, two. So this is propanoic. And then that's how you get your answer. So it's ethanoic, propanoic, anhydride. And then I sort of have a mechanism here for how anhydrides are created. So I have my acid catalyst, then that makes this alpha carbon for the carbonyl even more susceptible to a nucleophilic attack. And then as a result, the double bond between that oxygen and carbon, it'll break, and the lone pair will be on that oxygen again. Then it can collapse the oxygen, the lone pair can collapse and kick off the hydroxyl group. So then you're left with a positively charged carbonyl group, which is not good. Three bonding pairs, one lone pair. And then some base can come and take off that hydrogen. And you're left with an anhydride. Woohoo. So these aren't derivations of carboxylic acid, but they're also really important that you need to know. So amines are kind of alcohols, but N they have nitrogens instead of oxygens. So you have primary, secondary, tertiary, and quaternary. So how I like to think about amines, and this is also true for alcohols too, which I forgot to mention, is that just think about like how many R groups are attached to it. So primary, there's one R group. Secondary, two R groups. Tertiary, three R groups. And quaternary, four R groups. So primary amine is also known as an amino group. So amino as an amino acid, which I have here. So it's RNH2. And yeah, that's kind of all I want to talk about amines. And then I have imine, not to be confused with amine. They really got creative with all of it. And then there's amide, which is not to be confused with amine. But a bunch of tongue twisters, but amines are carbonyls, but instead of having an oxygen double bond to that carbon, you have a nitrogen that's double bonded to that carbon. And it can have like, yeah, like two R groups, one R group, whatever. It is what it is. But yeah, that's kind of all I want to talk about for functional groups. Yeah, hopefully that made sense. And if I made any egregious errors, please let me know in the comments. Once again, my name's Chacha, and thanks for listening.